Okay, so in this video, we want to solve the same problem as in the previous video, but instead of using a set of horizontal rectangles, we will use a set of vertical rectangles. So if you remember, we had the following region in the first quadrant of the xy plane, bounded by the curves y equals root of x, y equals 2, and the y-axis, and we revolve this region about the vertical line x equals -1. This generates this very nice solid of revolution, and we're trying to compute its volume. So now let's attack this with vertical rectangles. If you recall in the previous video, we used horizontal rectangles, which generated for us little washers, and we obtained a volume of 176 over 15 pi units cubed. Let's see, hopefully here, if we get the same answer. Okay, so our rectangle is vertical, so it's positioned along the x-axis. And the width of the rectangle is an infinitesimal change along the x-axis. Of course, it is given by dx. And now, if you think of it, instead of revolving the entire region about the axis of revolution, we will revolve, right, here's the region in the xy plane, and as we revolve it, we get the solid, but now we'll revolve something simpler. We'll revolve just a little rectangle lying within our region, and if you notice, the rectangle is away from and parallel to the axis of revolution, and again, because the width is infinitesimal, you can really think of the rectangle as just a really thin piece of string, and as you revolve the rectangle about the axis, this will generate a cylindrical shell. Which you can always think of as an aluminum can where the top and bottom are missing. And again, the center of your shell, of your aluminum can, is the axis of revolution. And you can clearly see that this is the rectangle. Or you can think of it as this one. As you revolve the rectangle that is away from and parallel to the axis of revolution, you generate a cylindrical shell. And again, we think of this rectangle having an infinitesimal width, so it really is just a thin aluminum can where the top and bottom is missing. So if you remember, to find the volume of this shell, we need three quantities. First, the thickness of our shell. This is, of course, the width of the rectangle dx. We need the height of our shell. This is the height of the rectangle. And then we need the radius of our shell, the distance between the center of the shell to the rectangle. Well, let's first find the height. So again, the height of the cylindrical shell is the height of the rectangle. So the height of this rectangle is a segment along the y-axis. So we need, and again, because we have a dx, everything we measure must be a function of x. So we have a line segment along the y-axis. To find its length, we need the larger y value and the smaller y value, and then subtract will give us the answer. So this is our height. Well, the larger y value here is constant. It's always y equals 2. So larger y value minus the smaller y value, but here we are on the curve y equals root of x, and so y as a function of x is root of x. So y is 2, y is root of x. 2 minus root of x gives us the length of the rectangle, the height of our shell. What about the radius? Well, if you look, the radius is again the distance between the center of the shell to the rectangle, but the center of the shell is in the xy plane, the axis of revolution. And the rectangle, of course, is the rectangle. So this line segment is your radius, the distance from the axis of revolution to the rectangle. It is a segment along the x-axis, and to find the length of this segment we need the bigger x value, but the rectangle is a generic rectangle and is positioned along the x-axis, so the x value here is x, and the left-hand point is simply the axis of revolution where x is -1. So the length of this segment is quite simply x, larger x value minus the smaller x value of -1, which is simply x plus 1. So now we have all the measurements in terms of x, and we can find the volume of our cylindrical shell. If you remember, the trick was simply to cut through one side of the shell open, and then you flatten it out against the page, and by doing so, the cylindrical shell becomes a rectangle. And the volume is obtained by finding the area of the rectangle times the thickness. The area will be the height h times the length, but the length of the rectangle is the circumference of the shell, which is 2 pi r. So length of the rectangle, circumference of the shell times the height, gives you the area of the rectangle times the thickness gives you the volume. And then we have r and h, so everything is okay. And now you can imagine, now I won't draw this one, it's a little messier, but this little cylindrical shell is within the full solid, right? Instead of revolving the full region about the axis of revolution, we revolve instead a tiny portion of it, a little vertical slice of it. And as you revolve, not the full region, but just a slice of it, a vertical slice of it, and as you revolve this rectangle now about the axis of revolution, you will generate this simple cylindrical shell within the full solid. And of course, to get the total volume of our solid of revolution, we have to sum the volume of all of these little cylindrical shells within the full solid. Of course, summing is integrating. So we have to sum the volume of our cylindrical shells, 2 pi r x plus 1 times the height, 2 minus root of x. And thinking again here of the power rule, I will replace root of x by x to the 1/2 dx. So we're summing the volume of all of our little cylindrical shells that are found within the full solid. But where do we start our summation and where do we end our summation? Well, this is quite easy, right? The cylindrical shells within the full solid are generated by our little rectangles within the region in the xy plane. So where do they begin? Well, we are summing with respect to x, and the rectangles in the region begin here, where x equals 0, and they go all the way up to here, where x equals 4. So we have to sum the volume of our cylindrical shells within the full solid as x goes from 0 to 4. And this will give us the full volume of the solid. And now this is the very easy part. We can use the fundamental theorem of calculus. So it will be pretty straightforward. The 2 pi is a constant multiple, so factor it out. 2 pi, we integrate from 0 to 4. Here we have a product between two functions of x. We cannot integrate over a product, so the only way out here is to multiply. We'll have x times 2 is 2x, minus x times x to the 1/2. We add the exponents. 1 plus 1/2 is 3/2, plus 1 times 2 plus 2, plus 1 times negative x to the 1/2, negative x to the 1/2. There is no possible simplification, so now we can use the fundamental theorem of calculus, finding our antiderivative. If If you integrate 2x, you get x squared, minus power rule here, add to 3 half 1 half, you get 5 half, and you must divide by 5 half, which means multiplying by 2 over 5, plus the integral of 2 is 2x, minus again the power rule, add to 1 half, 1 you get 3 half, divide by 3 half, multiply by the reciprocal 2/3. So this is our antiderivative, and we have to evaluate the antiderivative as x goes from 0 to 4. So we get 2 pi. Now we replace x by 4, so what do we have? 4 squared is 16, minus 4 to the 5 over 2. Take the square root of 4 first, gives you 2. 2 to the 5 is 32, times 2 is 64. So minus 64 over 5, plus 2 times 4 is 8, so plus 8, minus, and here again, 4 to the 3 half, take the square root first. Square root of 4 is 2, 2 cubed is 8, 8 times 2 is 16, so minus 16 over 3. Of course, minus the same antiderivative, 2 pi times this expression when x is 0, but if you replace x by 0, everything vanishes, and you get nothing. So this is the end result, and now let us simplify, and hopefully we'll get the same answer that we obtained in our previous solution using washers instead of cylindrical shells. So we can add first the integers. So 16 plus 8 is 24. And now we have minus 64 over 5, minus 16 over 3. So here, we can put these over a common denominator of 15 and do the same thing with 24. So what's going to happen here? If you think of it, if you multiply 24 by 15, think of it as 10 times 24, which is 240, and 5 is a half of 10, so a half of 240 is 120, and if you add 240 with 120, you get 360. This is simply 24 times 15, minus, we want this to be over 15, so by 3 over 3, now 3 times 60 is 180, plus 3 times 4, 12, means 192. Minus, to get this over 15, multiply by 5 over 5. 5 times 16 is 80. By over 15, sorry, yep. 5 times 16 is 80. So minus 80. This is all over 15. Equals, well, 2 pi times, well, let's see, we have 360. And if you add 180 with 190, sorry, with 180 you get 270, 272. So 360 minus 272 over 15 equals 2 pi times. But 370 minus 272 is 88, right? 270 plus 80 is 350 plus 8, 360. And now you can multiply by 2. 2 times 80 is 160. 2 times 8 is 16. 160 plus 16 is 176 over 15 pi, which is the same answer we obtained using washers instead of cylindrical shells. And that's it.